We rely on the physical force of pressure constantly to power tools, inflate tires, and operate heavy machinery, yet we rarely stop to question what that force actually is. To our human scale, a tank of compressed gas feels solid and perfectly stable, but according to the kinetic theory of gases, this apparent stillness is a complete illusion. Inside that heavy steel cylinder is mostly empty space, populated by a swarm of disconnected particles flying in absolute chaos. How does that erratic, microscopic void produce the rock-steady, measurable force we read on a dial? If we zoom in past the solid steel walls of the tank, we enter a microscopic world of perpetual, violent motion. The force we call pressure is the macroscopic measurement of trillions of microscopic physical impacts occurring every fraction of a second. To prove exactly how this works, we need to mathematically bridge the gap between human-scale physics and atomic reality. We have to track the journey of a single isolated particle and then scale that math up to encompass billions. Understanding pressure requires abandoning our everyday intuition and looking closely at the mechanics of a single microscopic bounce. We start our model by isolating just one gas molecule inside a simple three-dimensional cubic container. Let's focus on a particle traveling horizontally. We'll label its velocity v sub x as it flies directly toward the right-hand wall on the YZ plane. We treat this impact as a perfectly elastic collision. The molecule strikes the barrier and ricochets backward with the exact same speed, just in the opposite direction, giving us a final velocity of negative v sub x. To find the molecule's total change in momentum, we subtract its initial momentum from its final momentum, leaving us with negative 2mv sub x. Because momentum is conserved, the exact amount lost gets deposited straight into the wall as a positive 2mv sub x. One tiny particle transferring that sliver of momentum generates an effectively meaningless amount of force, but it gives us the structural building block we need. To measure a physical force, we need to know how many particles are actually striking a specific area within a given window of time. We can map out a literal strike zone, a subvolume sitting flat against the wall. Any particle inside this specific zone, moving at our speed v sub x, is guaranteed to hit the barrier before our timer runs out. We count the total particles in this zone using a metric called number density, represented by n. Since movement is random, on average, only half of the particles in this zone are actually flying toward the wall. When we multiply the momentum of a single impact by that active half of the particles in our strike zone, we calculate the total momentum transferred to the wall. Force is the rate of momentum transfer over time. By dividing our total momentum by our time interval, the timer drops out of the equation entirely, leaving us with the continuous force applied to the surface. Finally, we divide that physical force by the area of the wall itself. This gives us our first definition for pressure. P equals the number density times mass times the velocity squared. We derived the pressure exerted by one highly specific group of molecules moving identically along a single axis. Now we solve for scale. A physical tank of gas contains a massive distribution of molecules flying at wildly different, completely random speeds and angles. Because the velocities vary so drastically, we must sum up the contributions from every distinct group of particles and calculate their average squared speed. This is where we rely on a concept called isotropy. Inside a stable container, a gas has no preferred direction of travel. The microscopic chaos is perfectly statistically symmetrical across three-dimensional space. Because of that perfect symmetry, the average squared speed of molecules moving along the x-axis is exactly equal to those moving on the y-axis, and exactly equal to those on the z-axis. Each accounts for exactly 1/3 of the total speed squared. By relying on the statistical symmetry of trillions of erratic particles, the impossibly complex variables of three-dimensional chaos collapse down into a simple, elegant fraction. We swap that fraction into our formula to arrive at the ultimate equation of the kinetic theory of gases. Pressure equals 1/3 number density times mass times mean squared speed. This final variable acts as the definitive mathematical stand-in for the swarm's kinetic energy. This strictly theoretical derivation matches the macroscopic reality we experience every day. If you pump more gas into a tank, increasing the number density, or heat the tank up, which increases the mean squared speed, the physical needle on the dial ticks upward. That unyielding, rigid force against the container walls is the relentless, dynamic drumbeat of an invisible storm.